Okay, okay.
Okay, sir.
Shall
I'll
we
just
please
give
check,
a brief introduction
your
and then
voice is
shall we start?
not audible. രണ്ടാമതൊന്നുകൂടെ റീലോഗിൻ ചെയ്യൂ അത്. ഒന്ന് എക്സിറ്റ് ചെയ്തിട്ട് ഒന്നുകൂടെ ലോഗിൻ ചെയ്യൂ സൈബി.
Yes, sir.
Okay, okay, please.
I think I'm audible to the participants.
Has raised your
So,
hand.
Yeah, yes, ma'am. Yes, ma'am.
yeah. So we have Dr. K.V. Radhakrishnan. He has.
Nothing is audible to me from your side. Okay, fine. Okay,
so
fine.
he has done his B.Tech Chemical Engineering from Government Engineering College, Thrissur, and M.Tech Chemical Engineering and PhD from IIT Madras. So he currently serves as the professor and head Department of Biotechnology and Biochemical Engineering, Sri Chitra Tirunal College of Engineering, Papanamkoda, Trivandrum, Kerala. And he served as the principal of the same college. And he started his career with Central Public Sector Industry at Kochi as assistant engineer and worked with the work there for more than 2 years. And he then joined at TKM College of Engineering as lecturer in chemical engineering and held the positions of assistant professor. And he retired from TKM College 2018. And he served as the professor and head of Department of Biotechnology and Biochemical Engineering at Mohandas College of Engineering, Trivandrum, during the year from 2004 to 2006. He has more than 60 publications in international journals and conferences, and he has so many invited talks. And he has edited one book chapter published by Elsevier. He served as the reviewer of international journals, conferences, and chaired many technical conferences. And he has guided more than four PhD students at the University of Kerala and currently guiding one PhD student at CSIR NIST. He served as the member of Faculty of Engineering and Technology at University of Kerala, and he's a fellow of Indian Institute of Chemical Engineers. He received an award from the Ministry of Commerce and Industry, Petroleum and Explosive Safety Organization of Government of India in recognition of serving as a member of Enquiry Commission constituted by the Government of India to inquire into the Paravur Puttingal Temple fireworks accident that took place over 10 April 2016. He received Excellence Award from TKM College of Engineering and served as the member of 21-member National Executive Council of the Indian Institute of Chemical Engineers with headquarters at Kolkata in the period 2018 to 21. He is serving as an expert member of LWM and SWM Technical Committee of Kerala State Shuchitwa Mission, Government of Kerala, and he is serving as an expert member of Kerala State Pollution Control and Award Judging Committee for 2 teams, Government of Kerala. He is also a member of Hazardous Waste Incident Response Team of Kerala State Pollution Control Board and served as the member of Publication Committee of the journal Indian Chemical Engineer. And he served as the chairman of IACHE Trivandrum Regional Chapter, also member of Board of Governors in TKM College of Engineering, Kollam.
Hello.
And he's a consultant to process industries and offered consultancy services in the area of industrial safety. So I welcome Dr. K.V. Radhakrishnan to the talk.
So shall I start?
Yes, sir, you can start. Yes, sir.
Is the screen visible? Is the screen visible? See, I'm not getting any response from your side.
Can any other participant try speaking? Maybe my problem.
Now it is. Please make a comment whether you can. Screen is audible, visible.
Screen
Is it
is
visible?
not visible, sir.
Now, please respond.
Screen is not visible,
Just
sir.
tell me now whether it's visible. Is it visible?
Not visible, sir.
Is it visible?
No. No. Not visible.
I'm not getting any
Not visible,
response
sir.
from your side.
So your screen is not visible.
Between. ഇല്ല എന്റെ ലാപ്ടോപ്പ് മ്യൂട്ട് അല്ല എന്റെ ലാപ്ടോപ്പ് എനിക്കൊന്നും കേൾക്കാൻ പറ്റുന്നില്ല.
Still not visible, sir.
എനിക്ക് അല്ല ഇപ്പൊ ഞാൻ ബ്ലൂടൂത്ത് കണക്റ്റഡ് ആണോന്നോ?
Hello.
ഞാൻ ഒന്ന് നോക്കിക്കോട്ടെ. ബ്ലൂടൂത്ത് കണക്റ്റഡ്. ഹെഡ്സെറ്റ് കണക്റ്റഡ് ആണ്. ഹെഡ്സെറ്റ് ആണ്. ഇപ്പൊ കേൾക്കാമോ? അവിടുന്ന് കാരണം ഞാൻ അവിടുന്ന് കിട്ടുന്നോ ഇല്ലെന്ന് അറിയാതെ ഞാൻ അങ്ങനെ പ്രസന്റ് ചെയ്യണം. അതുകൊണ്ടാ. സൈബി, ഹലോ സൈബി. സൈബി ഇപ്പൊ കേൾക്കാം. പക്ഷെ എന്താ പ്രശ്നം? ബ്ലൂടൂത്ത് ഒന്നും കണക്റ്റഡ് അല്ലല്ലോ. ഒന്നും കണക്റ്റഡ് അല്ല. ഞാൻ ഈ സ്ക്രീൻ വിസിബിൾ ആണോ എന്ന് പറയൂ. ഈ സ്ക്രീൻ വിസിബിൾ ആണോ എന്ന് പറയൂ. ഹലോ.
Not visible, sir. Yes, visible.
സ്ക്രീൻ വിസിബിൾ ആണോ?
Now it is visible, sir.
Now visible. Now it's
Hello.
visible, sir.
ഹലോ.
സൈബി, നമുക്ക് സാറിന് ഓഡിബിൾ അല്ലേ? സൈബിക്ക് കേൾക്കാൻ
ഞാൻ
പറ്റുന്നില്ല.
തുടങ്ങട്ടെ. എനിക്ക് അവിടെ നിന്നൊന്നും ഇല്ലാത്തത് കൊണ്ട് എനിക്ക് എന്താണ്
സാറിന് നമ്മൾ പറയുന്ന സൗണ്ട് സാറിന് കേൾക്കുന്നില്ല എന്നാണ് എനിക്ക് മനസ്സിലാവുന്നത്.
ഒരു സെക്കൻഡ്. ഓക്കെ. ഇതെന്താണ്?
ഹലോ സർ. ഹലോ രജീഷ്. അതാ ഞാനൊന്ന് നോക്കട്ടെ, ഞാനൊന്ന് വിളിച്ചു നോക്കട്ടെ സാറിനെ തന്നെ.
അല്ല മ്യൂട്ട് അല്ല.
ആ
ഞാൻ ഹെഡ്സെറ്റ് ഇല്ലാതെ ഇപ്പൊ എന്തെങ്കിലും കേൾക്കാമോ? ഇപ്പൊ ഞാൻ പറയുന്നത് കേൾക്കാം, ഇങ്ങോട്ടൊന്നും കേൾക്കാൻ വയ്യ.
സാർ ഇപ്പൊ ഞങ്ങൾക്ക് കേൾക്കാം. സാർ
ഒരു സെക്കൻഡ്,
കേൾക്കാമോ?
ഞാൻ ഒന്നുകൂടെ നോക്കട്ടെ. ഇനി സൗണ്ട് മ്യൂട്ട് ആണോ നോക്കട്ടെ, സ്പീക്കർ മ്യൂട്ട് ആണോ നോക്കിക്കോട്ടെ. അല്ല, സ്പീക്കർ മ്യൂട്ട് അല്ല, 100%. ഒരു സെക്കൻഡ്. അല്ല, ഇപ്പൊ സ്ക്രീൻ വിസിബിൾ ആണോ? ഇപ്പൊ വിസിബിൾ ആണോ? ഓക്കെ ഓക്കെ. സൈബി, ഒരു സെക്കൻഡ് ഇവിടെ ഒന്ന് ഹോൾഡ് ചെയ്യും. ഞാൻ ഒന്ന് ഹെഡ്സെറ്റ് ഒന്ന് മാറ്റി നോക്കാം.
സൈബി സാറിനോട് സ്റ്റാർട്ട് ചെയ്യാൻ പറഞ്ഞോ? സൈബി എന്താന്ന് വെച്ചാല് സാറിന് കേൾക്കാൻ പറ്റാത്തത്. സൈബി ഫോണിലല്ലേ, ഞാൻ വിളിച്ചിട്ട് സാറിന് കിട്ടുന്നില്ല.
Dear participants, please wait for a second. Sir will join in another 1 minute.
സ്പീക്കർ വയ്ക്കാൻ പറ്റില്ല.
ഹലോ.
സാർ ഓഡിബിളോ?
Sir, കേൾക്കാം sir.
ഞാൻ ഒന്നുകൂടെ നോക്കാം. ഞാൻ ഒന്നുകൂടെ നോക്കാം കേട്ടോ. ഒന്നുകൂടെ നോക്കാം. ശരി ഓക്കെ. റീജോയിൻ ചെയ്ത് നോക്കട്ടെ.
Sir, you can start via audible.
So you are muted, I think. Please unmute.
Yeah, okay. Am I audible now?
Yes sir, you are audible.
Okay. Yeah.
ഇപ്പൊ കേൾക്കാമോ? Sir,
ഇപ്പൊ
കേൾക്കാമോ?
കേൾക്കാം. ഓക്കെ.
Okay.
ഇപ്പോ സ്ക്രീൻ വിസിബിൾ ആണോ എന്ന് പറയൂ.
വിസിബിൾ അല്ല സർ, സ്ക്രീൻ ഷെയർ ചെയ്യാമോ?
ഇപ്പോഴോ?
Not sir.
Yes, sir.
Not?
Yes sir. Yes, yeah.
Okay, okay. Yeah, okay. So now let us start. Okay. Sorry for the initial hiccups. Yeah, good morning, one and all. Thanks to Dr. Saibi, the coordinator of the FDP, and all of the other former colleagues of my parent department for inviting me to this FDP to deliver a lecture on the low carbon fuels. I'm happy to note that this Atal FDP on sustainable energy and carbon neutrality is being organized by the Department of Chemical Engineering at TKM College of Engineering. The topic selected also is highly relevant, and I hope that the deliberations that take place in this FDP would throw light on the various aspects of the adoption of novel technologies for the energy transition from fossil fuels to greener fuels. We also know that the global energy sector is witnessing a paradigm shift in the recent years. We are also aware that the entire world is making every effort for the transitioning of their energy to a sustainable energy future. So in this context, harnessing sustainable energy resources is receiving much attention in our country as well as in many other countries. It is an established fact that the adoption of fossil fuels in conventional energy systems has led to the increase of the concentration of greenhouse gases in the atmosphere. Of course, this led to the climatic changes, the rise of ocean levels, and many other catastrophic effects. And we are all experiencing the adverse effect of this. The adoption of renewable energy has also increased rapidly due to the low environmental impacts. A clean and carbon dioxide free system can be realized to improve the quality of human life, and this is the need of the hour. Hence, a transition from fossil fuels to greener fuels is inevitable in the next few years for the existence of the Earth. But how to proceed with the low carbon future fuel technologies is really a difficult task, as many challenges come in our way for this transition. We largely depend on fossil fuels, and these fossil fuels cannot be phased out all of a sudden.
Sir, are
Yeah.
you changing the slides?
No, not changing.
Okay.
This is only in the
Sorry.
introductory slide. Yeah. I'll move on to the slides now. Okay, hence the stakeholders and proponents of fossil fuels, especially in the oil and gas industry, advocate for a staged approach to energy transition and economic transition. So my topic of this FDP is on low carbon future fuels, emerging roles in the energy transition. So the industry people advocate for developing carbon capture storage technologies to enable the production of new energy carriers, including the hydrogen from the fossil fuels like natural gas. But we know that this carbon dioxide produced as byproduct will have to be captured and suitably restored rather than being emitted. But the carbon capture and storage technologies, which we call it as the CCUS, pose many challenges. This include technical, economical, social, and regulatory challenges. Natural gas has been the world's largest energy source in the mid-2020s, and the petroleum resource companies have a different perception that the blue hydrogen, which is considered as a bridging technology before the full transition to low carbon fuels like green hydrogen adoption. So these technocrats argue that the investment in blue hydrogen by integrating possible future fuels like hydrogen with the natural gas networks and further investment in storage facilities would be a welcome step. So definitely a trade-off between the adoption of the carbon capture and utilization systems and the transition to low carbon sources and new energy carriers with viable technologies, economically viable technologies is required at the moment. So my attempt is to bring to you the various aspects of the low carbon future fuels. But touching on all this, I would rather delve into the basic aspects of the hydrogen to be used as an energy carrier, along with the very fundamental properties, its major uses, and the different types of storage systems and its safety aspect. So these are the things that I would like to share with you prior to proceeding with the talk. So the contents of my talk is structured in such a way. I think the screen is visible to you. Am I?
Yes, sir. Yes, sir.
Yeah. So these are the contents that I have organized for the presentation. So to begin with, I will be talking on the prominent low carbon future fuels, and then moving on to the hydrogen, its characteristics, properties as an energy carrier, and also the pros and cons and the different types of storage systems. So this is what I would like to share with you in this talk today. So actually what is being given is an approach to decarbonizing with the future fuels. So we know that the low carbon fuels are alternative fuels that release significantly lower greenhouse gases compared to the conventional fossil fuels like coal, gasoline, or diesel over their life cycle. So these low carbon fuels play a crucial role in decarbonizing the hard to abate sectors. That means majorly the industry sectors, the aviation, shipping, and the long haul transport sector. So a pragmatic approach to decarbonization is to have a step-by-step pathway to decarbonize the sectors that cannot be easily electrified using low carbon energy sources. So the target sectors are the hard to electrify sectors, which include the sectors that I have already mentioned, like the aviation and heavy industry and shipping. So many of these sectors are really hard to electrify or to replace with the low carbon fuels. So the approach here is to go for future fuels that help reduce the emissions without compromising on the performance, and also to maintain and preserve the operational benefits. And also we have to encourage the use of an existing infrastructure that avoids massive technology changes. So these steps enable low carbon future fuels in the hard to abate sectors. So the idea is not to reinvent everything from scratch, but to gradually shift towards the fuels that emit less carbon dioxide and the fuels that preserve the energy density needed for the operations, and also utilize the current and existing infrastructure without the technologies being completely overhauled or revamped. So such a pragmatic approach accelerates our transition to a low carbon future. So by definition, we can say that the low carbon future fuels are the energy carriers designed to replace fossil fuels in the hard to electrify sectors, so while reducing the greenhouse emissions. Now, what are the prominent future fuels? Of course, there are a host of prominent future fuels. Out of this, hydrogen comes at the top. I think discussions have taken place in this FDP on hydrogen. So please excuse me if there is any repetition of the contents. So hydrogen or we can say that green hydrogen produced through the electrolysis using renewable energy sources is considered the cleanest and the alternative fuel. So its production process involves using electricity generated from sources like solar, wind, hydropower to split water molecules into hydrogen and oxygen. So these are the very fundamental things which every one of us know about it. The absence of carbon emissions during both the production as well as the combustion stage to make it an environmentally attractive option. So that is about the hydrogen part. And next comes the ammonia, which is also a low carbon fuel, emission fuel, future fuel. So ammonia is often synthesized from the hydrogen and nitrogen through the well-known Haber-Bosch process. So the traditional Haber-Bosch process actually relies on fossil fuels, but using green hydrogen in this process results in green ammonia. So ammonia also offers advantages over pure hydrogen in terms of storage and transportation, because it is easier to liquefy this ammonia and transport it in bulk compared to the hydrogen. And the third one is the prominent future fuel is biofuels. You know, this has been discussed in almost wherever the discussions on energy takes place. Biofuels take a prominent role. So biofuels are derived from biomass, waste materials, or dedicated crops, offering a renewable alternative to fossil fuels. They can be produced from a variety of feedstocks, including agricultural residues, energy crops, municipal solid waste. And as to the types of biofuels, we have the biodiesel. You know, it is produced from the trans-esterification of the vegetable oil, animal fats, or recycled greases. This can be used in trucks, ships as a substitute for conventional diesel fuel, or often blended with petroleum diesel. And again, bioethanol is produced through the fermentation of sugars or starches derived from the crops like corn or sugarcane or cellulosic fibers, cellulosic biomass materials. And this is also typically used in cars and blended with gasoline to reduce the emissions. And the fourth among the prominent future fuels is the sustainable aviation fuel. This is designed as a drop-in replacement. That means we can have a momentary replacement of the existing fuels with the sustainable aviation fuel, provided this is refined appropriately. So this aims at reducing the carbon footprint of the air travel sector. So the sustainable aviation fuel must meet certain stringent specifications to ensure compatibility with the existing aircraft engines and infrastructure. So another class of future fuels is the e-fuels. They are called as electrofuels. So e-fuels, they are also known as electrofuels, or can be considered as a synthetic fuel. So this is created by combining the green hydrogen with the sequestrated or the captured carbon dioxide. So the carbon dioxide can be captured from industrial sources or from the or directly from the air using direct air capture technologies. So the resulting fuels are chemically identical to the fossil fuel counterparts, allowing them to be used in existing engines and infrastructure without subjecting it to any modifications. So there are various types of e-fuels. There are the e-diesel or e-gasoline. These are all similar to the petroleum products of diesel and gasoline, or e-kerosene, which is a different version of the sustainable aviation fuel, which is a synthetic alternative to conventional kerosene-based jet fuel produced by combining the green hydrogen with the captured or the sequestrated carbon dioxide. Okay. Now comes. Now let us take these one by one. So coming to the hydrogen, we can see hydrogen is, there are different colors of hydrogen, from green hydrogen, blue hydrogen, gray hydrogen. Green hydrogen offers zero emissions from, and it is produced from renewable energy sources. And the blue hydrogen, it is having a lower emissions compared to other black hydrogen, because whatever the carbon emissions generated are being captured here in blue hydrogen. And the green hydrogen, which is having a highest carbon footprint, it is produced from the natural gas sources or LNG. So hydrogen is a versatile energy carrier that can be produced from various sources, including renewable energy, natural gas with carbon capture, and also from nuclear power. So when this hydrogen is used in fuel cells or combustion engines, hydrogen produces water as a byproduct. So this makes hydrogen a potentially zero emission fuel. So as to green hydrogen, this is produced through electrolysis using renewable energy. Blue hydrogen, it is produced from natural gas via the steam methane reforming route, SMR, with the carbon dioxide produced being sequestrated or stored. And the gray hydrogen provides a translational solution to the use of future fuels with a significant reduction of greenhouse gas emissions, because the green hydrogen is produced from natural gas via the SMR route without carbon capture. But it is not considered as a low carbon fuel, because the raw material that we use is the natural gas. And now we have some other colors of nitrogen, which are brown and black and brown hydrogen. And these black and brown hydrogen are produced from coal gasification without any carbon capture technology. So the distinction between black and brown is, the black hydrogen is produced from bituminous coal, whereas the brown hydrogen is produced from lignite. As to the process, this is produced by the coal gasification, which involves reacting the coal with steam and oxygen at high temperatures to produce a mixture of gases, including hydrogen, carbon monoxide, and carbon dioxide. So further, it has to be separated using appropriate methods. And as to the emissions, this method is the most carbon intensive way to produce hydrogen, as all the carbon dioxide generated is released into the atmosphere. So nothing is being captured in the black hydrogen segment. And now we have the purple or the pink or red hydrogen. So this is produced by the electrolysis of water using renewable energy. And next is the yellow hydrogen. Yellow hydrogen is produced using a mix of energies. You can use grid electricity using fossil fuels, and also you can couple with other renewable sources of energy. So the hydrogen produced in this way, we call it as yellow hydrogen. And another is the turquoise hydrogen, which is also obtained from the, it is produced from the methane pyrolysis. There is no emission of carbon dioxide. The entire carbon form is converted into the pure solid form. So the pyrolysis of this methane is done to convert this methane to carbon and hydrogen in the form of solid form of carbon and hydrogen. So this methane pyrolysis involves heating methane to a high temperature in the absence of oxygen, and causing it to decompose the hydrogen and solid carbon. So this process has potentially low emissions because it produces solid form of carbon dioxide as a byproduct instead of carbon dioxide. So the solid carbon dioxide, which in turn can be used for a host of applications like soil amendments, or even this could be used as a construction material. But this technology is under development. I would say either it's the research stage, It's still under the development and not yet commercially widespread. Next form of hydrogen, next color of hydrogen is the white hydrogen. Of course, this is the geological form of hydrogen. This is available in, it is said that recent reports were there that this form of hydrogen is available in some geological formations in some countries as hydrogen seeps. So this white hydrogen is not produced through any industrial process, but is extracted directly from natural sources. So the emissions associated with white hydrogen are also primarily related to the extraction and purification. That means the form of energy that we use for extraction of this source of hydrogen. So if we use renewable energy sources for extraction of hydrogen, this is this form of hydrogen or this color of hydrogen doesn't have any emissions. Now, okay, moving on from hydrogen, we can go to the sustainable fuels. So what are the sustainable fuels? Sustainable fuels, you can categorize a fuel as a sustainable fuel if it adheres to some stringent regulations set by the US or the Europe standards. So for the fuel to be fully or truly sustainable, it has to meet some requirements. That means it has to avoid, some of the conditions are, it has to avoid the land use change. That means we should not use any raw material which causes deforestation or habitat loss. And secondly, we have to use non-food feedstocks wherever possible. And thirdly, we have to reduce the life cycle greenhouse gas emissions fully during the entire life cycle of this fuel. And also it has to be a part of the circular bioeconomy. That is another condition. And also the use and consumption of water and fertilizers, that also needs to be minimized. And these fuels have to comply with the regulations like the European Union RED II, that is the Renewable Energy Directive, and another regulation of the US, that is the Renewable Fuel Standard, US RFS. So these are the two major regulatory frameworks that govern the production, blending, and sustainability of biofuels in the European Union and the United States. So now the pathways to the renewable energy. So we know that the biofuels are renewable fuels derived from biomass, offering a potential alternative to fossil fuels. So they are categorized in different generations based on the feedstock and production technology. We have the various generations from the first generation biofuels to the fourth generation biofuels. So as to the first generation biofuels, we know that they are produced readily from available feedstocks. Actually, this classification depends on the type of feedstock that are used. If you use sugars, starches, and vegetable oils for the production of bioethanol, this can be categorized as the first generation biofuels. So this is primarily produced through the fermentation of sugars or starches. So the most common feedstocks that have been in use were the sugarcane and corn. So there, because of that, there were some controversies associated with that. And another first generation fuel, that is the biodiesel, which otherwise we call it as the fatty acid methyl ester, FAME. And they're produced through the transesterification of the vegetable oils or animal fats or recycled greases. So this process converts oils into biodiesel. Okay. Now comes to the second generation biofuels. They're also known as the advanced biofuels, and they are produced from non-food feedstocks. We don't use any food feedstocks for this. So we use lignocellulosic biomass. The major raw materials that we use are the corn stover, wood chips. So because of this, the second generation biofuels are also called as lignocellulosic ethanol. And these are produced by the fermentation of sugars derived from the lignocellulosic biomass, like agricultural residues, forestry resources, waste materials and energy crops. So the advantage of this is this type of the secondary generation biofuels do not compete with the food crops and has the potential for higher greenhouse gas emission reductions. Okay, then the third generation biofuels we have, they are produced from the algae and other advanced feedstocks. We know that the microalgae or macroalgae produce oils and carbohydrates, and this oils and carbohydrates can be converted, which oils we call it as the lipid fraction. This can be converted into the biofuels. The advantage is the algae can be cultivated to produce oils that can be converted into biodiesel or biocrude oils. So another advantage is this algae have higher growth rates and can also be grown on non-arable land. This makes them a potential feedstock for biofuel production. And now comes the fourth generation biofuel. They are called as the carbon neutral, or even they can be carbon negative as well. There is no emission of carbon in different forms. So here we use the concept of synthetic biology approaches to modify the microorganisms. So by bringing genetical modifications on the microorganisms and combine. So we combine the bioenergy and the carbon capture technologies. So both will be there. So since we are using both the bioenergy that is it is being used by the microorganisms and the carbon capture technologies, this can be considered as carbon neutral or carbon negative technology. So some of the technologies are, we call it as the BECCS technology, BCCS technologies. That means bioenergy plus carbon capture technologies. So these are the different generations of the biofuels. Now the pathways. What are the pathways to attain the sustainable biofuels? The pathways these refer to the different technologies or technological and biological routes used to produce biofuels from renewable biological sources like plants, agricultural waste or crops, algae, or even municipal waste. But we have to ensure that low carbon emissions and sustainability across the life cycle of the product. So bioethanol, we know, as it has been mentioned, it is by the fermentation to convert the sugars into ethanol using enzymes or microorganisms. So that's the route that we adopt in the bioethanol production. So which involves the pre-treatment, enzymatic hydrolysis, and further fermentation. And so for bioethanol, this also can be used in blending with the gasoline or petrol. In India also we have set some targets for the blending of bioethanol. That is currently we use in 2024 the percentage of bioethanol that is to be mixed with petrol was 20%. But in we have nearly reached this target around 19% last year. And the Bureau of Indian Standards, the use of another is the biodiesel, where the Bureau of BIS standards have been evolved for the use of or the specifications of the biodiesel blending. So we have the various codes available, IS 17021, which specifies the codes and standards for the blending of diesel from B6 to B20. B6 means 6% biodiesel can be blended with the diesel, and up to 20%. But we have not been able to attain this target so far. Hardly we could attain less than 2% status in the blending process. Next is another technology on the low carbon or the future fuels is the power to X technologies. Power to X technologies. So on the left side is power, and on the right side you can have X. X could be anything. So power to X technologies, which are called as the PTX technologies. So this refers to a family of processes that convert the surplus renewable electricity, mainly from solar, wind, or hydropower, into energy carriers or fuels or useful chemical products. That means whenever we have surplus amount of energy, this could be used for converting it or using this energy to produce chemical energy carriers and fuels or even chemical products. And so this concept is increasingly important in the transition towards a low carbon economy. This technology enables the sector coupling, that means connecting the power sector with the transport sector or the industry sector and also the heating application sector. So here in the power to X technology, power means that is the electricity generated, especially from renewable energy sources, because the renewable energy sources are intermittent. So whenever we have surplus energy, this energy could be used to convert this energy into energy carriers, fuels, or useful chemical products. So there are many technologies available under this heading, and out of this, some of the technologies I would like to talk on. That is the power to gas technologies. So that means the conversion of electricity to the gases. So PTG, we call it as the PTG, power to gas. So this technology involves using electricity to split water into hydrogen and oxygen through electrolysis route. So the produced hydrogen can then be used directly or further processed into other gases. The hydrogen and oxygen that we get from the electrolysis. Hydrogen could be used as raw materials from many other sources, or it can also be used directly. And as to the pathways within the power to gas sector are the hydrogen production. That means electrolysis technologies. We can adopt alkaline, various types of electrolysis processes using alkaline electrolysis or PEM electrolysis, solid oxide electrolysis, these to generate hydrogen. And then we have on the other side, hydrogen we have produced. Next is the carbon dioxide. So that means carbon dioxide, or we can also use ammonia also in the methanation process. So the methane can be injected into existing natural gas grids used for heating or as a fuel for transportation. So the carbon dioxide you can capture from the industrial sources, and hydrogen we have already obtained the direct capture or from the sequestration from the industrial emissions. So we have hydrogen and carbon dioxide. Essentially, these are the two raw materials for you can either use it as such or you can convert this to many other products. And next is the P2L technologies, power to liquid technologies, which are called as PTL technologies. They convert renewable electricity into liquid fuels. This offers a drop-in replacement of the conventional fossil fuels. So this the products that we get are e-methanol, e-diesel, and e-kerosene. All are hydrocarbons. So that means the power is used to convert it into hydrocarbons. Next is the power could be used P2X technology. Under this, we have power to chemicals, electricity to chemicals. This generates methanol, ammonia, and many other olefins. And another technology that comes under the power to X technology is power to heat. The power to heat involves converting electricity into heat. That is quite common. So this can be done. This can be used for various applications, including direct heating, industrial process, or residential heating in cold climates, and also power to mobility sector. That is one of the major sector is the hydrogen or the e-fuels, which offer many advantages in the transportation sector. And now we have how this power technology is implemented. Power to X technology is implemented. This power to X technology, what is the pathway for this? So the pathway for converting the intermittent renewable energy into storable chemical fuels, P2X. So this approach is used whenever we have surplus energy or whenever we have energy available with intermittency. It is the situations that we know that the solar and wind are available all the time. So it is available only from selected times. So producing excess energy and then storage of the surplus energy for a later use. So this could be beneficial. In such cases, we resort to the power to X for low carbon fuels. And these involve 4 steps. Mainly, these involve 4 steps. First is electrolysis. Electrolysis, mainly we focus on the hydrogen from water electrolysis. So hydrogen, this green hydrogen becomes, we get the green hydrogen from the electrolysis, that becomes an energy carrier. And next is the carbon dioxide. This carbon dioxide can be obtained from many other sources, from industrial sources, but we do it from, in power to X technologies, we only use the captured carbon dioxide, either through direct air capture or from industrial emission, industrial flue gases. So capturing the hydrogen as well as the captured hydrogen. We have 2 raw materials available. And then the third step involved is synthesizing it. Using this hydrogen and this carbon dioxide, we convert it to chemically combine it to produce various chemicals, that is e-methanol, e-fuels, e-methanol, e-diesel, methane, or other synthetic hydrocarbons. So that's the third step, synthesis. And once we produce it, we move on to the 4th stage. That means we have to store it. That means the storable chemical fuels. These are also synthetic fuels. They are energy dense fuels. So the storable form of fuels have a good amount of energy storage potential. And so having got such a high energy density, we use it for, it is transportable because a large amount of material could be stored in a small amount of space. So we can also use existing infrastructure, and we can also use the surplus energy for a later use. So these are the steps, the pathways for P to X technologies. So in this technology, we focus, we pay some attention on the ammonia under this power to chemical sector, because this is being largely discussed nowadays, and it is just this technology has got acceptance in the recent past in many sectors. So ammonia is a chemical carrier of hydrogen. We know that ammonia, the molecular form of hydrogen, is NH3. It comprises of nitrogen and hydrogen. So ammonia acts as a chemical carrier of hydrogen through a process that involves synthesizing the ammonia from the hydrogen and nitrogen, the raw materials. And further, it is transporting this ammonia. And then whenever we want it, this ammonia has to be cracked back to hydrogen and nitrogen. That means at the point of use. So the production of ammonia typically involves, as I mentioned earlier, the production of ammonia is by the Haber-Bosch process, which is a well-established industrial process. But it may not necessarily use the hydrogen that is obtained from the renewable sources. But here in this segment, that is the power to chemicals, we have to use only renewable energy sources for the production of hydrogen. And so it could be used by tapping or by using the solar or wind or any other form of this energy resources can be used to produce green hydrogen. And next raw material is the nitrogen. That's the key nitrogen, which is the key element of this ammonia. So nitrogen is obtained from the air separation process. We know that air contains 79% by volume of nitrogen and 21% by volume of oxygen. So this air is subjected to liquefaction and cryogenic distillation to produce nitrogen from this air. And this this nitrogen obtained from this cryogenic distillation, which is combined with the renewable or green hydrogen in the same process, that is the Haber-Bosch process, to produce ammonia. Then it becomes the green ammonia. So the Haber-Bosch process actually it involves reacting this separated nitrogen and the green hydrogen at high temperatures, that's about 400 to 500 degrees Celsius, extremely high pressures to the tune of about 150 to 250 bars. And in the presence of a catalyst, so we know the reaction also. The nitrogen plus one mole of nitrogen combines with 3 moles of hydrogen, giving 2 moles of ammonia. So once this ammonia is produced, ammonia can be transported in various forms. We can leverage the existing infrastructure for this, because already many transportation methods are available for transporting this ammonia to fertilizer industries. In many countries, we have transportation of ammonia is done in pipelines. And also, these pipelines can be repurposed or expanded to transport ammonia for hydrogen energy application. And another form of transport is using ships. Ammonia can be transported in liquid form via ships, similar to the LPG that we do, or the liquefied LNG or LPG. But this is a cost-effective option for long-distance transportation, especially across oceans. And then it is stored. Once it is transported, it is stored at the destination or the point of use. So this ammonia can be stored in large storage tanks at terminals or distribution centers. So these tanks can be designated to maintain the ammonia in liquid form at moderate pressures and temperature compared to hydrogen. So now at the point of use, we have to get hydrogen. So for that, the cracking of ammonia has to be done. Anyway, this cracking of ammonia again, that means conversion of the ammonia at the point of use into nitrogen and hydrogen, back to nitrogen and hydrogen. This also involves the consumption of energy. But remember that we have to use only non-renewable renewable energy sources for this cracking of ammonia back to nitrogen and hydrogen. So the cracking process involves passing this ammonia over catalyst. So catalytic cracking at high temperatures to the tune of about 700 to 900 degrees Celsius by using various catalysts like nickel or ruthenium or iron-based catalysts are prominently used. And of course, the choice of the catalyst also affects the efficiency and the cost of cracking process. And so the resulting hydrogen could be used in the point of application. That means we can directly use it fuel cells or hydrogen in fuel cells to generate electricity by combining. And so water is the only product that is obtained in this. So ammonia is a potential future fuel. As to the advantages and the merits and demerits, it is as to the merits, ammonia is carbon free. Ammonia combustion process produces no carbon dioxide. That means it is facilitating the decarbonizing sectors like power and transport sector. We can largely depend on this ammonia in power and transport sector. And it has got a higher hydrogen intensity. The formula of ammonia is NH3. Around 17.8% by weight of ammonia is this hydrogen. So this can be stored easily because the temperature needed for the liquefaction is only minus 30 to 33 degrees Celsius for ammonia compared to that minus 253 degrees Celsius for hydrogen. Ease of storage also is there for the ammonia storage. And also, it's ammonia is the energy obtained is versatile. The versatility of this energy that also is there. So ammonia can power engines, turbines, or fuel cells directly. So this also offers diverse energy solutions. And as to the disadvantages, there are many production challenges. Because the production of ammonia or green ammonia is energy intensive. It requires significant energy and which are impacting its carbon footprint. So we have to strictly use the renewable forms of energy. And also the safety concerns. Ammonia, it is toxic and corrosive, and this poses safety risk in handling and storage. And also another important disadvantage with ammonia is, conversion of ammonia or partial oxidation of ammonia at the point of use can result in NOx emissions, nitrogen dioxide or nitric oxide emissions. And also we do have the disadvantage of the infrastructural gaps. We have the existing infrastructure, but still to go on a large scale application of this ammonia, these gaps remain in ammonia distribution and the refueling networks. So these are about ammonia. As to the applications, it can be used as a shipping fuel, the direct fuel in ships, and power generation. We can use it directly in power plants, and this is used in fertilizer plants. So now the pathways, pathways, as I have already mentioned about the production pathways of ammonia. The main method is the Haber process, but the only thing is we need to use renewable forms of energy to produce hydrogen as well as nitrogen. And so we can synthesize this green ammonia. But this process is energy intensive and carbon intensive. So green ammonia production using renewable energy sources like wind or solar or hydro to power the electrolysis of water to produce hydrogen. That is the only way out, and to be used in the Haber process. So the energy, the form of energy that is used in the Haber process has to be fully renewable in nature. Okay. So some other emerging methods are also coming in. The electrochemical and thermochemical processes. They have improved efficiency and reduced emissions. Such pathways are also available. So we can say that ammonia has a large role to play in the sustainable energy segment. So it is used in power generation. It is used in transportation, industrial heating application. And ammonia is used as a medium for renewable energy storage and transporting renewable energy. So now comes following this ammonia, we have the e-fuels. This also I have already mentioned about this. So we have the e-fuels. This represents a promising pathway for decarbonizing sectors that are difficult to electrify directly. So the segments include the aviation sector or shipping sector. So by utilizing the captured carbon dioxide and green hydrogen to create liquid fuels, e-fuels are electrofuels. Many different form of e-fuels are available, like as I mentioned, e-methane. E-methane is there. E-methane, the process is e-methanation, electromethanation. That is power. It comes under the power to methane, P2X. Power to methane is a process that produces synthetic methane using renewable electricity, water, and carbon dioxide. So using renewable electricity from water, you generate hydrogen, and then carbon dioxide, you have to use the captured carbon dioxide from industrial sources or from the atmospheric sources. So the main steps involved, one can infer that what are the processes involved. It's nothing but the electrolysis process to produce green hydrogen using renewable energy sources, and the methanation reaction. Methanation to synthetic methane. Synthetic methane, we use carbon dioxide as a raw material. The process is just a battery process, a battery process, where the green hydrogen is reacted with the carbon dioxide, the captured carbon dioxide to produce methane and water. So we know that the reaction also, it is the reaction given as the carbon dioxide plus 4 hydrogen molecules giving methane and 2H2O. But the reaction is highly exothermic and occurs on, it's a catalytic reaction taking place on a nickel-based catalyst at high temperature of 250 to 400 degrees Celsius. Okay, so in a similar way, we can generate e-gasoline or e-kerosene from sustainable aviation fuels. So this is the process for the e-methanol process. Methanol process. You have to capture the carbon dioxide. The hydrogen you have to produce it electrolytically, combine it in catalytic conversion process reactors. You can generate methane. But here also you need separation of this methanol from other gases. So this is the e-methanol pathway. And you know, methanol has got many applications. E-methanol has got a wide range of applications across different segments. That means it is used as a fuel additive with methanol blended with gasoline. You know, as I mentioned, methanol blending with gasoline. Our country also is in these lines to promote the blending. So year by year, we are increasing the percentage of the methanol blending in the gasoline or the petrol. So this is a common practice in many countries, which is used as a sustainable alternative to fossil fuels, which is even for reduction of greenhouse emissions. So our country also has formulated various policies under this National Policy on Biofuels, which was formulated in 2018 and then updated in 22. The target of the blending was 10%. In 2022, we have achieved this 10% blending in 2022, and now it is 20%. It is called E20. It is 20% anhydrous methanol blending target by 2030. That is the target set. But actually, originally it was set for 2030, but now it is accelerated to 2025. So as e-methanol has got many other, it is used as a chemical feedstock for many different applications. And e-methanol can be converted into formaldehyde, acetic acid, then methyl tertiary butyl ether. This is used as an additive in gasoline. But now in many countries they have banned this because the use of methyl tertiary butyl ether as an additive in gasoline, that is banned because that is soluble in water. It reaches over water bodies very easily. So this I would say that e-methanol can replace fossil-based methanol in these applications and reduce the carbon footprint of the chemical industry as well. And this is, as I said earlier, e-methanol can be used as a direct fuel in modified combustion engines. We already have methanol fuel vehicles which offer lower emissions compared to gasoline vehicles, and e-methanol can further reduce the carbon footprint of this transportation segment. And e-methanol also is used in the marine fuel segment. This is also gaining traction as a marine fuel due to its lower emissions compared to the heavy fuel oil that was used earlier. So this is a sustainable alternative for the shipping industry, and this helps to reduce the environmental impact. Then, as to the advantages and the challenges, as to advantages, it has got, as I said earlier, it has got versatile applications, has lower emissions, and it can be stored as a liquid fuel. It is again another advantage of this methanol. And the challenges include the production cost, because since we are using renewable forms of energy, definitely I would say that with course of time, this we can bring down the costs associated with the production of e-methanol. And the energy density of methanol has a lower energy density compared to gasoline or petrol or diesel. It has got lower energy density methanol. We shall see the numerical figure of this energy density later. So that means we need a larger fuel tanks to store it. In a given space, you can accommodate only less amount of methanol because its energy density is less. And another disadvantage, negative point, is the corrosivity of this methanol. Methanol can be corrosive to various materials. So that means this requires modification to the fuel systems and engines. And next is the kerosene synthetic aviation segment, we normally resort to the production of synthesis gas. Then which this is in the Fischer-Tropsch process. All chemical engineers must be aware of the Fischer-Tropsch process. We can produce many chemicals in the syngas production. And if you want to get the sustainable aviation fuel, further refining and upgradation also is required in this. That means purification, because it has got stringent conditions to be used as a sustainable aviation fuel. So the applications of aviation fuel, it's a direct replacement of the conventional jet fuel. This allows for the seamless transition to move to a sustainable aviation sector. So it is used in existing aircraft engines and without subjecting the existing infrastructure to modifications. And e-kerosene also has got many advantages. It is used as a drop-in fuel. That means e-kerosene can be used in existing aircraft without modification. That is one of its advantages. And it has got reduced emissions. It significantly reduces the emissions in the emission of gases, greenhouse gases in the aviation sector. And that's the disadvantages or the expensive nature of the production, that is it, compared to the conventional jet fuels, the petroleum sources. And also scalability issues, scaling issues, challenges. Scaling up the production of e-kerosene to meet the demand of the aviation sector. Actually, this requires significant investments in infrastructure technology. So these are the challenges involved. And now comes which segment has to be used? What are the factors to how to choose this type of fuel for which application? So you have this a metrics market segment. It's called as a market positioning metrics for low carbon and fuels. So some of the observations are ammonia is used in the shipping sector. It is very suitable for maritime use due to the ease of storage and the energy density. But it has got a limited versatility outside shipping segment without major infrastructure changes. So the use of ammonia is currently limited to the shipping sector alone. And hydrogen, of course, hydrogen has got a versatile application. It can be used in decarbonizing the industries, especially the steel making industry. We know the emissions taking place from steel making industries or steel industries enormous. So actually, we use hydrogen to produce energy to decarbonize the steel industries using direct reduced iron process. So currently the hydrogen that is used for reduction of iron oxide, this is from what you call from petroleum resources. So that has to be changed to the green hydrogen sources. And next observation is the use of synthetic aviation fuels. Actually, it is used in some niche areas of applications, largely restricted to aviation sector. But this is also critical in that particular sector for decarbonizing the aviation sector. And hydrogen also has got another versatile application, the chemical feedstock segment, which is in ammonia production, methanol production, in petroleum refining operations. Yes, green hydrogen has got extensive applications. So these are the observations. So what shall be the pathways? In conclusion, I can say that what shall be the pathways for sustainable energy future? So the production and utilization of low carbon fuels, they are essential for achieving deep decarbonization across various sectors of the economy. So the availability and cost of renewable electricity are the critical factors, and these factors definitely influence the viability of these fuels. We have the power to X technologies. They offer a promising solution for integrating renewable energy into the energy system and also creating for valuable energy carriers. We can produce any energy carriers like hydrogen or ammonia or methanol, methanol. So different low carbon fuels are suited for different applications. And of course, understanding the specific applications is crucial for effectively deploying these fuels and maximizing their decarbonization impact. So we have to exercise caution in the use of fuels in the transition to the low carbon fuels. So we require continued innovation, we require investment, we require policy support, and also to scale up the production processes and the utilization of low carbon fuels and accelerate the transition to sustainable energy process. And now let us see the pathways to net zero. Every one of you might have heard of the net zero. It is largely discussed nowadays. We have said various countries have set their targets. So we know that the net zero emissions means reducing greenhouse gas emissions as much as possible and removing or offsetting the remaining emissions. So reduce the greenhouse gas emissions and also removing or offsetting the remaining emissions. So the total emissions added to the atmosphere equals zero. Total carbon emissions that are added to the atmosphere have to be zero. So as of now, around 140 countries have announced their net zero goals. For example, the European Union, they have set their targets by net zero by 2050, China by 2060, and India also has set its target to 2070 and 2070 to limit the global warming to 1.5 degrees Celsius compared to the pre-industrial area. So the world is moving to a net zero carbon dioxide by around 2050. According to the, we can say that the India government, IPCC, Intergovernmental Panel on Climatic Change. And also, many companies and corporations also have got their own roles, and they also have pledged their net zero by specific dates. They have set targets with specific dates, aligning to their operations. So they also declared that, okay, their operations will be changed to renewable energy sector, and also in their supply chains to climatic goals to control the climatic changes. So what shall be the pathway to net zero? So a strategic roadmap has been devised, including the factors, many factors. So there is an urgency for survival of the humanity. That means net zero emissions are to be implemented as early as possible to mitigate the climatic risk. That is one of the roadmap. And the decarbonizing electricity, we have to decarbonize the electricity. We should not depend on the fossil fuels. So decarbonizing the electricity by combining the renewables plus storage options, either combining the renewable energy plus the storage options or nuclear energy to create carbon-free electricity. So that is one of the strategies of the roadmap. Next is the entire economy has to be electrified using clean electricity. So this clean electricity has to be used to power the industries and also the transport sector. You know, the transport sector is the main sector that contributes to the global greenhouse gases. And also to, in buildings, heating or cooling of the buildings is not so common in our state. But of course, we also normally use air conditioners in almost in 20 to 30% of the homes. So next is the carbon, addressing the carbon emissions in the major polluting industries, carbon polluting industries like steel industries. We have to control the carbon emissions in the steel industries, cement industries, again at another major industry that contributes to the greenhouse gas emissions. Again, fertilizer industries, the shipping, aviation industries. This cannot be fully electrified. So that means we have to limit the carbon emissions in these industries. by adopting a stage-wise procedure. Another option is we have to enhance the role of green hydrogen as a key solution for decarbonizing these sectors. So these are the roadmap. Okay. Of course, India has also set its emerging targets by and taken a leadership role in this. Many targets have been set. Many missions have been like the hydrogen. Even I'm not delving into various aspects of all these missions. Anyway, we do have our share in this, in controlling the climate changes. Like ambitious, we have set our ambitious renewable energy goals, the promotion of electric vehicles, and also the national green hydrogen mission, and the electrification of the economy, and the net zero commitment by 2060. These are some of the leadership roles that India has already taken in this direction. Now comes last part of this presentation, that is on hydrogen. Why we have to go for the hydrogen economy? Hydrogen is a versatile energy carrier. This is produced from various sources, including renewable energy, natural gas with carbon capture and nuclear power. And this can be used in fuel cells, LP engines. Hydrogen produces water as a byproduct. So it is potentially a zero emission fuel. And this is abundant, the most abundant element in the universe. Hydrogen makes up about 75% of the elemental mass of the universe. And most of the forms that exist as hydrogen gas in stars, where the main fuel for nuclear fusion is the sun. We have the hydrogen, and 90% of the number of atoms in the sun is hydrogen. So in general, we can say hydrogen. The sun contains 74% in hydrogen and 24% helium by mass. So hydrogen is not an energy source by itself, like fossil fuels or sunlight, but it is more like a battery. It stores and delivers energy. So we use this energy usually for electricity, which is ideally renewable, to split water into hydrogen and oxygen via electrolysis, and stores the energy from the electricity. So we can release the energy by combining the hydrogen and oxygen in a fuel cell and burning it to produce the byproduct water. So hydrogen is one of the secondary energy sources, I would say, which produces no greenhouse gas emissions by byproducts during its either in the utilization stage or in the oxidation stage. So there is no harmful emissions in this. And this is hydrogen is a part of water molecule. Fossil fuels are hydrocarbons and many other organic matter. It is found in pure form. The lightest element with a density of about 0.089 kilograms per meter cube. But the density could be increased by increasing the pressure to 70 megapascal or 700 bars. This is the common pressure that we use in hydrogen cars. So if it is liquefied, the density goes up to 70.8 kilogram per meter cube at minus 253 degrees Celsius. That means about 800 times compared to the uncompressed form of hydrogen. And then this so why hydrogen is used? I mean, as said earlier, hydrogen is an abundant and clean fuel with hydrogen energy content. So it has got a gravimetric energy content of about 122 to 142 megajoule per kg. Remember, this is much higher compared to the diesel or fuel that we use. This is the energy content, the gravimetric energy content is about of hydrogen is about 3 to 3.5 times that of the conventional fuels that we use. As said earlier, combustion of hydrogen does not produce any carbon dioxide. So hydrogen has got a global acceptance as an environmentally safe fuel. Now, looking at the properties is of hydrogen is very important. I will touch upon these properties and some of the very important properties that are essentially to be looked at. I think that will only be discussed here. So its boiling point is about minus 252 or 253 degrees Celsius, which comes about 20.28 Kelvin. So hydrogen has a very low boiling point, and so it necessitates liquefaction at cryogenic temperatures for efficient storage and transportation from the liquid form. So cryogenic storage is required. And heating value, it has got a lower heating value of about 120 megajoules per kg. That means 33.3 kilowatt hours per kg. That means every kg of this hydrogen can generate about it is 33.3 units of electricity. So hydrogen possesses one of the highest energy content per unit mass compared to all of the fuels. And on the higher heating value, I'm not explaining what exactly is higher heating value or lower heating value. This is higher heating value, that is with the vaporized water vapor component. It has got a higher latent heat of vaporization. So the heating value increases. Higher heating value is 142 megajoules per kg. And as to the minimum ignition energy, that is also, it is very less. That is 0.02 megajoules. Hydrogen has a very low minimum ignition energy. That means it can be ignited by even small sparks or static electricity. That means that poses many issues with the handling. Okay. Then the flammability range also is high, 4 to 75% by volume. Hydrogen has a wide flammability range. That means it can ignite and burn at compositions between 4% hydrogen to 75% hydrogen. So that means stringent safety measures need to be exercised to prevent the leaks and control the potential ignition sources. Okay. So the small leaks can form dangerous mixtures because the explosive limit is between 18% to 59% by volume of hydrogen. And it produces a very high temperature flame, to the tune of about more than 2000 degrees Celsius. So hydrogen combustion produces a high temperature flame. So this is highly beneficial for certain applications, but also requires appropriate materials, because to tolerate this 2000 degrees Celsius, we have to use appropriate materials to withstand the heat. And also the detonation range, that is explosive unit I already mentioned. So the detonation is highly destructive. So we have to be careful about handling of this. Okay. So in general, we can say that hydrogen has a very high diffusivity and permeability. So it can easily escape through very small pores and many materials. We cannot use the conventional materials for storing this hydrogen. This requires specialized sealing and compactable materials. And it can cause burns because the flame is invisible. Sometimes it is pale blue. And but the radiant heat also is low. Radiant heat. You never get hurt if you approach near to that. But direct exposure is hazardous. So flames may be difficult to see. You cannot, flame is not visible. So you have to use either UV detection systems or IV infrared sensors. They are highly essential. And also the burning velocity of hydrogen also is very high, to the tune of about 2.65 meter per second. You can see per second the flame propagates at a speed of about 2.65 meter per second. Compared to methane, methane flame propagates only about 40 centimeter per second, whereas hydrogen flame propagates about 2.65 meter per second. So hydrogen, it can cause detonations are more violent in this. And also another problem with hydrogen safety is the cryogenic hazards, the liquid hydrogen, because we use extremely cold conditions. This causes frostbite. We use minus 253 degrees Celsius in the storage as liquid hydrogen. So frostbite and cold burns, and also hydrogen embrittlement of materials. And also in the cold storages, it causes the boil off and pressure build up because it gets evaporated very fast. So storage systems require pressure relief valves. Then sometimes oxygen enrichment risk also is there. Cold hydrogen can condense atmospheric oxygen. That means the atmospheric oxygen will be deprived of the required amount of oxygen for our breathing purposes. So creating an oxidizer enriched surface which is prone to violent ignition. And again, the material compatibility. Material compatibility is very important. We use special stainless steels, special aluminum materials, having high strength steels are preferred. Even the gaskets and the seals that we used, many of the elastomers that we commonly use in other applications, hydrogen is permeable in all these materials. So we have to use special purpose materials for this. And this table gives a comparison of the volumetric energy density with respect to many other fuels. So we have hydrogen, methane, propane, and ammonia. So out of all this, what are the observations in terms of the volumetric energy density? You know, at ambient conditions, hydrogen has an extremely low volumetric energy density. That means 10.8, it has got a volumetric energy density of 10.8 megajoule per meter cube, which is actually far below methane, propane, or ammonia. This volumetric energy density is very less. But when compressed to 350 to 700 bars or liquefied at cryogenic temperatures to minus 253 degrees Celsius, hydrogen acquires a higher volumetric energy density to the tune of about near about 5,000 or 4,500 to 8,500 megajoules per meter cube by refrigeration systems. But this is also again significantly lower than those of liquid hydrocarbon. We can achieve the liquid energy, the energy densities to the tune of about 5,000 megajoules per meter cube by cryogenic compressing and cooling. Whereas, you know, this liquid hydrocarbons has got an energy density of 22,000, more than 22,000 megajoules per meter cube. And liquid propane that we use for our domestic application, that has got a higher energy density to the tune of 25,000 megajoule per meter cube. Even ammonia has a volumetric energy density of 11,500 megajoule per meter cube. So that is one of the limitations of this hydrogen. But I can say that this table gives a comparison of the gravimetric energy density. So hydrogen has got an excellent gravimetric energy density. So gravimetrically, we can say we have to strike a balance, great balance between the weight and the volume. And we can say that gravimetrically hydrogen is the king, but it's very light. So volumetrically it is poor. So unless compressed or liquefied. And this is the liquefaction temperatures. We know hydrogen and methane, you know, the pressure to which to achieve this liquefaction is 123 bars we require. That means normal materials cannot support this hydrogen storages. Even for methane, it's only 46 bars we need to reach its liquefaction temperatures. So that's why we use special purpose materials for storing this. And in terms of explosive limit, this gives a comparison of the explosive limits of various fuels. So hydrogen, the limit is the range between the lower flammability limit and upper flammability limit. That's the flammability range, we call it as it is between 4 to 75%. Whereas acetylene is it's only it's between 2 to 100 percentage. So in conclusion, we can say that hydrogen exhibits good engine performance. It exhibits flame propagation length and improved power output. A larger explosive limit has advantages for performance, especially in combustion systems. So they are used in rocket engines. Hydrogen used in rocket engines because of the larger explosive limit. And the higher inflammability range, this means higher safety risk. So this requires robust handling, storage, and detection systems. So there has to be a trade-off between all this. So that means it's great for controlled energy systems, but potentially hazardous if not managed properly. So as I said earlier, hydrogen is, in a nutshell, we can say that hydrogen is an energy carrier. It's not a primary energy source. It is derived from many other sources. So hydrogen can be considered as a secondary source. It's an energy carrier, stores energy and transports energy. And the challenges are many in the segment in terms of hydrogen storage. Different storage technologies are used. We have compressed hydrogen storage to enhance the density to 42.2 kilogram per meter cube. If we compress it to 700 bars, then it is used in mobile transport in trucks, rails, and underground pipes. The liquefied form of hydrogen storages are available, provided you compress it down to minus 253 degrees Celsius. There are many other storages. There's secondary chemical carriers are ammonia, and then another chemical storage, liquid organic hydrogen chemical storage. They are called as LOHCs because it's liquid. Some of the liquids can absorb this hydrogen, and then this hydrogen absorbed could be retrieved at the point of use by providing additional energy to it. Then another form of energy carrier, that is ammonia. This is also a chemical form of hydrogen storage. And methanol is again a chemical form of hydrogen storage. And we use also metal hydrates. Metal hydrates is another storage. Okay, now then I will wind up in another few minutes. Okay, as for storage now, storage of hydrogen as a gas we require pressures to the tune of about 350 to 1250 bars. That's the tank pressure desired for if you want to use it in buses, we can use it at 350 bars. And if you want to use it for cars, the pressure range involved is very high because only a small amount of storage volume is can be made available in a car to run large distances. So in liquid form, it has to be cooled to cryogenic temperatures down to minus 253 degrees Celsius. And hydrogen can also be stored on surface of solids like metal hydrates or within solids by absorption. Many technologies are available. These are some of the storage systems available. They are physical based, also material based. In physical based, you can compress the gas and cold compression techniques or liquid form. In material based, we have many technologies available. We can have adsorbents, metal organic frameworks. They are available to store hydrogen. Liquid organics, many liquid organic systems are available to store this. Then metal hydrates, different form of metal hydrates like complex hydrate, chemical hydrogen systems, industrial hydrogen systems are available. These systems have got its own merits and demerits. Okay, this. So in general, we can say that the physical storage methods such as compressed gas and liquid hydrogen are technologically mature, and they can deliver higher densities, but demand either extremely high pressures or cryogenic temperatures. So this leads to energy intensive and complex storage systems. But material-based storages like adsorbents or liquid organic hydrogen compounds or in metal hydrates or chemical storages, These problems include volumetric efficiency, safer handling issues, and integration with existing liquid fuel infrastructure. But however, we can say that these approaches are still limited by the slow kinetics. This metal hydrates, they have kinetics involved, is very slow. So higher regeneration temperatures we need while regenerating this hydrogen from these hydrates, we require higher regeneration temperatures. And because of the incomplete reversibility, it means we cannot retrieve a complete amount of hydrogen that has been absorbed in this metal nitrate. So chemical hydrogen storage refers to materials or compounds that store hydrogen in a chemical form. That also is available. So then further, this can release hydrogen through chemical reaction. They are not reversible. The storage systems are not reversible because it is already transformed to another form of chemicals. So these are the comparison of energy efficiencies. So choosing the right hydrogen storage system is also very important. So we use for stationary applications, we use metal hydrates or chemical hydrates because it has higher volumetric storage efficiency and safety and stability, good safety and stability issues. And but it is, as it is heavy, it is not suitable for mobile use. And then in the mobility sector, what is recommended is we have to go for composite pressure cylinders to tolerate the pressures to the level of 350 to 700 bars. And also cryogenic tanks, transportation in using cryogenic tanks. That also is used in the mobility sector or the transport sector. Because they have got higher gravimetric efficiency and why they are widely used in fuel cell electric vehicles. There, but the disadvantage is, you know that the lower volumetric efficiency means it requires more space. And for long distance transport and flexible storages, so what is the type of storage mechanism that we have to depend on? We use LOHCs, liquid organic hydrogen carriers. That is a system normally used for long transport, flexible storage. Or we can go for methanol or ammonia or synthetic fuels because we can use existing liquid fuel infrastructure. We have a balance between the gravimetric and volumetric emissions. And we can also use lower pressure requirements. Okay, so we can have a comparison between the diesel and what you call this gasoline. So these two fuels, we know that they got high efficiency in both mass and volume. And this serves as a target reference for future hydrogen carriers. This I'll skip. So in conclusion, I can say that, so this is the transitioning to clean energy from the fossil fuel dependence. What the shift has to be gradual rather than a rapid shift. So we need to have a gradual shift with economically viable transition and the implementation of carbon capture and utilization systems, and then transitioning to blue hydrogen production. That is also needs to be promoted. And further, we have to move on the clean energy, carbon dioxide free energy system. This shall be the roadmap towards attaining the clean energy system. So in conclusion, we can say that the adoption of low carbon fuels is vital to achieving global carbon goals and securing sustainable energy systems. The emerging options such as green hydrogen, ammonia, biofuels, and synthetic fuels will definitely play a pivotal role in or across many sectors like transport, power, and industry. But the path to large-scale hydrogen deployment requires a phased approach. We cannot all of a sudden we cannot have a hydrogen economy. Although some roadmap has been drawn, even for Kerala government also has drawn the roadmap. They have started the Hydrogen Valley operations with the support of ANERT. So there has to be a phased approach with the blue hydrogen serving as a bridging technology. Blue hydrogen means the carbon sequestration methods. before moving on to the green hydrogen statement. So this enables immediate emission reductions while green hydrogen production and infrastructure scale-up has to be done. So there is no single, we can say that there is no single fuel that can address all changes, but instead we have to go for a portfolio of complementary low carbon fuels supported by technical innovation, carbon capture, storage, and also enabling policies. So this will drive the transition to the future fuels. So advancing through the blue hydrogen today, while preparing for a green hydrogen future tomorrow, shall be a pragmatic roadmap towards cleaner and resilient and net zero energy future. So this is all about my discussion. So thank you.
Thank you, sir.
Yes, thank you.
Does the participants have any questions? Sir, we have one question in chat box.
Okay, let me see.
What is the use of ammonia and its density for gas?
Pardon? Use of
What-
ammonia.
And its density for gas 0.73 or 730 kilogram per meter cube. Which one is correct? Use of ammonia.
Use of ammonia. Use of ammonia, that I have already mentioned, that ammonia is also a hydrogen carrier because the raw materials that are used for ammonia, it is hydrogen and nitrogen. So nitrogen has to be obtained from the liquefaction of air through by using alternate energy sources, and hydrogen from the electrolysis. So actually the energy density, I'm talking about the energy density. Energy density, it is about 11,000 megajoules per meter cube. Compared to that of LNG, it comes about more than 20,000 megajoules per meter cube. So we focus on the energy density rather than the normal density part. You know, hydrogen has a density of 0.09. That is the kilogram per meter cube. So ammonia will have slightly higher density. That's what I think, compared to that of. I've not exactly looked at what is the density because we focus on the energy density rather than looking at the normal density. Energy density is higher than that of hydrogen. Ammonia has a higher energy density. As I said earlier, hydrogen has energy density to the tune of about 4,500 to 5,000 megajoule per meter cube, whereas ammonia has got 11,000 megajoule per meter cube.
Sir, but gravimetric energy density is very less, na? That is based on mass.
Yes.
Then how can we use as a fuel, especially for a diesel engine or for a petrol engine? Because it's a very less compared with hydrogen also.
Yeah, for IC engines, there are systems available. They're called HICE systems, hydrogen IC engine systems. That is being extensively researched nowadays. Use of hydrogen in IC engines. But ammonia, I think researches are ongoing for use of ammonia as a fuel. I think such kind of initiatives are not.
Sir, most of the research studies are saying ammonia is unfit fuel for especially for IC engine because of its energy per mass basis. But based on volumetric density may be higher because it is used as a higher energy hydrogen energy carrier. So based on that only most of the people are recommending to use in IC engine also.
IC engines, normally this is not encouraged because of the corrosion issues. Ammonia.
Yeah, corrosion issue and also it's a toxic one.
Yeah, toxic because emissions of NOx, that is more
NOx
prevalent.
emissions will be higher.
NOx emissions will be more dominant in the case of ammonia.
Yes, sir.
But that's why it is limited to some niche areas, you know, especially in the shipping sector. That
Yes,
is
sir.
already,
Yeah.
that is already come up. The shipping cycle.
Sir, is there any possible to produce green ammonia? That means based on renewable energy sources. Is there
Certainly,
any?
certainly, we have the source, we have the raw materials, nitrogen and hydrogen now. Look,
Yeah.
As I said earlier, ammonia is produced using the Haber-Bosch process, where
Yeah, that is the
nitrogen and
fossil fuel.
hydrogen are reacted at high temperature and pressure. But in order to attain such a high temperature and pressure, we need to depend on energy sources. So this energy source has to be obtained from renewable energy sources. In that specific
Okay,
case,
sir.
we can produce green ammonia. Such initiatives are advanced now. But as far as a country like India is concerned, definitely large scale production, large scale dependence on this renewable source, especially solar energy, is coming to existence nowadays. No?
Sir, and also a gasification process also there not for producing both ammonia as well as hydrogen. Is there it's also one of the process only?
Yeah,
Gasification.
that partial oxidation is there. Partial gasification also is there. Partial gasification, steam reforming is
Yes,
done,
sir.
or partial oxidation also is done to produce hydrogen from ammonia.
Okay, sir. Thank you, sir.
Thank you. Yes, I think it is already. What's the time there? It is 9:26. I think. So for me, the time is around. What is the time? It is 10:57 in the morning. Okay.
Yes, sir. Then we will wind up the session, sir.
Okay.
Thank you, sir. Thank you for
Thank
the
you.
talk.
Thank
And
you. Thank you.
Ma'am, please share the PPT and as well as recorded video for especially for this session.
yes, sir.
Yeah,
We'll
I'll
share.
share the PPT to Dr. Saibi. Okay.
Okay, sir. Thank you, sir.
Thank you. Thank you. Bye.
Participants, please fill the feedback form for this session as well.
So what should I say?
Thank
Good night or good morning? Yeah. Okay. From my side, it is good morning, and your side, it is good night.
Yeah, it is good.
Thank-
night, sir.
Yeah. Thank you. Thank you.
Thank you, sir.